Okay, so what I'm going to try and do today, there's absolutely no way in 20, 25 minutes I can cover everything about organic phosphorus in soils, sediments and waters. So I think it's important to remember, I know the focus is on soils, but I'm going to try and give, as I'm aware that there are a number of people here who are possibly new to this, this particular topic, so I thought it would be good to look at a little bit of the history. And so, first of all, this is when I leapt into phosphorus 36 years ago. If only I looked like that now, it'd be great. I only uncovered this photograph a year ago. Somebody sent it to me. I think they were extorting money out of me. But anyway, in terms of organic phosphorus, and I'm going to be mainly talking about soil, but a lot of the techniques that we use in soils apply to sediments and to some extent in waters as well. And this is a diagram that, I mean, I know my name's on it, but it's actually Ben that put this together, and I think it's a really, really good diagram. It gives me a bit of a context of what I'm going to talk about, because the whole idea is to work in terms of trying to define poles, and that's the methodology, and then the real challenge is trying to link the poles together and to link the key processes that affect phosphorus in the various poles. So what I'm going to be talking about is really sort of three aspects. One is very quickly how you measure total organic phosphorus in soil. I'm not going to spend too much time on that. About the chemical nature, I'm going to spend a little bit of time on fractionation, and a little bit of time on speciation in terms of what sort of way we use that there. And then I'm going to talk a little bit about how we look at the dynamics of the flux. And phosphorus is not easy; it's like any other element, but in soils. But there are particular challenges in here that are basically ongoing. Now, it didn't come up too well. Never mind. In terms of total organic phosphorus, in terms of measuring it, we've known about organic phosphorus since really about the early 30s, and even before that, actually. But in terms of actually measuring it, it really only in the 50s and 60s. This came out of my thesis, believe it or not. And you just get the date here, they're all 1950s and 60s, and these are just a sample of the methods that were developed for extracting organic phosphorus. And they were actually based on the methods that were used to extract organic carbon from soil, to do humic acid and fulvic acid work. And they all relied on the reason why I've highlighted is that every single one of them has an acid pre-step in it. So that's sort of been carried on. And then there's the ignition method. So I think I've got the right date there, I think it might be 53. Saunders and Williams. It's a quick method. It's very good, but you've got to be careful about it because, for example, it doesn't work in well-weathered soils. And there were papers back in the 1960s that actually showed that you shouldn't use this method in anything strongly weathered because you'll get a really false result in terms of organic phosphorus. But nonetheless, it's a handy technique, and it's good. And then we go to fractionation. Now, I could spend the next 40 minutes talking about fractionation. In fact, I've actually done that at other conferences. But just to give you a brief overview of where fractionation comes from. The idea of fractionation is that you use a series of extractants of different types, whether it be neutral, acid, alkali, to separate phosphorus into different forms. And the original fractionation scheme was actually all about inorganic phosphorus, and it was all about looking at what happens to fertilizer, the fate of fertilizer in soil. And organic phosphorus was determined separately by using ignition. But the principle is actually the same in terms of what's come after it. And there are any number of variations on it. And I'll just show you the most famous one of all, which is the Headlee. Although when people talk about Headlee these days, it's only got a passing resemblance to this. And I even talked to Mike Headlee about it, I know Mike quite well. And, you know, the actual scheme that he developed had 10 steps in it, including microbial phosphorus, which was done on a separate sample. And it also included, very importantly, and there was the talk yesterday about aggregates, about the idea of looking at aggregate protected phosphorus. I don't know anybody who's doing that anymore in terms of a fractionation scheme. And very few people actually integrate microbial phosphorus into the system as well. But nonetheless, the thing that the Headlee scheme actually illustrates is the inclusion of organic phosphorus in these extracts. So the idea was that with the extracts you then included, there was no distinction between iron and aluminium, and there was a measure of inorganic and organic phosphorus. And then when you got past this step, he passed the acid, the calcium step, then you went into the so-called recalcitrant refractory phosphorus. And so basically there's been a lot of variations on that, right? And I think people should be careful about using the word Headlee when they talk about it. And then there's this method here, which I picked out of the bag, and it was a method that was specifically developed for tropical soils, because the Headlee method, this method commonly in most soils doesn't actually extract this pole at the bottom here is about 50% of the phosphorus. When you go to tropical soils, very strongly weathered soils, when you get to here, you're talking about maybe 20% of the extractable P. So the important step here, and I was involved in developing this, it's not only 12 molar concentrated HCl, but they do it at 70 degrees as well. Okay, so you're differentiating material on that basis, and then you can see. And then there's another variation on it, which is basically, there's two things here. One is it puts back in a salt extraction at the start. I'll come back to that in a minute. And it's got bicarbonate, sodium hydroxide, HCl, but it comes back to that organic matter extraction and puts a second sodium hydroxide in. And on some soils, not strongly weathered soils, weakly and moderately weathered soils, you can probably extract 90% of the phosphorus in that system. So that's the fractionation thing. That's the whole sort of principle of it, and it's constantly evolving and being used. And it's actually a relatively easy technique, and you know, for actually a reasonable, not a lot of work, you can actually get a lot of data. What you do with that data is another thing. But I think there's a danger here, and the one thing is that you've got to be damn careful when you're doing fractionation. You've got to have proper standards, proper references all the way through the system. And I think there's a tendency for, I've witnessed in my own lab as well, a tendency for some people to get a little bit lazy with this technique, and it can lead to all sorts of problems. But just to give you an example of its use, anyway, and I thought I'd go away from soils and go into, well, it's still soils, but it's a wetland system. This is in Florida, in South Florida. And what you're talking about here is basically the influence of phosphorus. It's basically a pristine environment. Total phosphorus in the water body, 9.8. And what you've got is phosphorus coming in from an agricultural watershed at the top of the Everglades and coming in and basically changing the vegetation and essentially changing the soil by that way. And if you look at what happens in terms of the phosphorus, and this is the distance from the inflow, this is the distance from when the phosphorus is coming in. So this here is essentially pristine, if you like, and then this is sort of phosphorus polluted. And I'm just pointing out the role that organic phosphorus plays in here, in terms of accumulation of that organic phosphorus. So in terms of driving the biogeochemistry in here, organic phosphorus is incredibly important. And that shows you the value of using the sort of fractionation. It can give you real good insights into something like that. But one of the cautionary notes about fractionation is that the assumption is that the harder it is to extract a phosphorus compound, or organic phosphorus, then the less available it is. It works to some extent, but nobody really told plants and microbes this, because they don't really care, to be honest. And if you go back to the original Headlee paper, which people quote as a method paper, but it was actually a study where they looked at native grassland in Canada and 65 years of wheat fallow with no phosphorus inputs. And of course this was going to draw down a lot of phosphorus. But if you look at the changes in terms of organic phosphorus, you can see here that about 30% decrease, and if you look at the residual phosphorus, and this was 50% of the phosphorus, the residual, the percent decrease was about the same, 30%. So basically, that would suggest that the plants were drawing down equally from these poles. But in fact, if you look at the percentage of the total P decline, 50% of the phosphorus that was taken up by plants came from this so-called recalcitrant pole. You know, so we just got to be careful about it in terms of interpreting it. The other thing about interpreting it, and there's a lot of stuff on this data, and this was a little lesson I learned myself, because this was from my PhD, and we were looking at, this is time along the bottom here, 30 years, and we were looking at different treatments in terms of using a fractionation scheme of this variety, which was adapted from the original Headlee. And we got this massive change in terms of these two poles between 1971 and 74. And we got this big drop in organic phosphorus 1, and we got this big increase in organic. And the papers in Journal of Soil Science, you can go and read it. And it was absolute fairy tale we were talking about, because we were coming up with all sorts of explanations in terms of calcium reacting with organic matter. It was a complete fallacy. It was an artifact. Because what happened was, when we put the lime in, of course, there was a lot of calcium in the system. And a bit later, Ken Perrott actually showed that, and he used sodium chloride wash, that if you don't put a pre-wash in, if you don't get rid of the cations at the beginning, then the distribution of organic phosphorus is completely different. He proved it with 2 different soils. So just to see here, you see that on this soil here with no pre-wash, you had 1,000, 200. With a sodium chloride pre-wash with no phosphorus extracted, you went to 1,189. So that went down by half, just because you didn't do that. So my recommendation, is the only thing I will recommend today, is that if you're going to do fractionation, put a salt at the beginning of it. And in point of fact, when we looked at this again, we went back to the 1960s and we actually found papers that had done this before in terms of inorganic phosphorus. In fact, that was the reason why they put that salt at the beginning. But it's very relevant for organic phosphorus. So that's one way of looking at the poles. The other way of looking at organic phosphorus is to try and look at its chemical nature. And the original work that was done on this, and it really was pioneering work, and I don't think it gets the recognition, to be honest, that it actually deserves, in terms of that we know what forms of organic phosphorus, they had an idea what was coming in. So in terms of what was in the soil, they then went looking for these compounds like inositol phosphates, phospholipids, DNA, nucleic acid. And the techniques are horrendous, right, in terms of complexity. And the reason why I know this is because I tried it when I started my PhD. This was how I was going to characterize organic phosphorus. And then in the space of 6 months, Mike Headlee, we heard through the grapevine that there was a new fractionation scheme coming out of Canada, so we got that. And we also happened to run into a guy called Roger Newman, who was actually doing NMR on phosphorus. And he said, we've got this new technique for looking at phosphorus. So I abandoned this and went to NMR spectroscopy. But nonetheless, these techniques are robust. They are very robust, but they're incredibly involved. And if you're, I mean, I'm a closet chemist, and if you like that sort of stuff, it's really, really good fun to do. But the thing about it is that basically, the idea was that there's 2 basic forms of main types of organic phosphorus in soil. There's the labile stuff, which is there's a diester where the phosphorus is connected to carbon chains by 2 links, and then so this is a nucleic acid, and this is monoester inositol hexaphosphate. And the idea was that this is sort of labile and this is stable in soil, relatively. And where they get that from, and this is going back a little way, is that if you look at, this is bacteria, fungi, plants, if you look at the sources of organic phosphorus coming into a soil and a sediment, you'll see that upwards of 80% is actually diesters of the organic phosphorus, and only 20% is monoesters. Yet when you look at the soil, these numbers need to be updated a little bit, but the vast majority is actually present in monoesters. So that suggests that these materials are not very stable in soil, whereas these are. And that's pretty much accepted. And Joe, I'm not going to talk too much about NMR, but when NMR came along, it did kind of revolutionize things a little bit, because it allowed us to quantify, not simply, it wasn't an easy technique. I mean, in those days, these runs took 24 hours. I know when I did them, I spent a whole week running NMRs, and how we met it. But the thing about NMR is you can actually quantify it. So you could actually quantify those peaks. And in the old days, the good old days, we used to take the scan of the machine, copy it onto A3 paper, get surgical scissors, and cut the peaks out and weigh them. I've still got them in a little bag, right? You weigh them to 4 decimal places, and that's how you worked out. But a couple of other things that pointed out, it gave you access not only to things like polyphosphate, which are quite hard to measure in soil, but it also proved that this material was present in soil, which was phosphonate. So it was a real advance, and there's going to be lots of talks about NMR in terms of how it's been used. But essentially, the detail around here has been refined a little bit, but in essence, it's basically the same. The machines are a lot better now, they're a lot faster, the extracts are hopefully standardized, I think, and it's a very, very useful technique. But there is one disadvantage to all of this: fractionation, what are you looking at, speciation, and that is that you're extracting it from the soil. As soon as you extract something from the soil with a reagent, there is a chance that not a chance, it's almost certain you're changing it. So you don't know whether that actually relates to what was actually in the soil. In the case of carbon, you will find very, very, very little work in the last 10, 15 years, anything to do with humic acid and fulvic acid in soil. Because carbon work is now based on solid state NMR. That's how they do, and other techniques where they actually do in situ analysis. And if we could get, to me the holy grail would be to actually get into soils, and I know there are emerging techniques that may allow us to do this. This is a solid state NMR of a soil. So this is unextracted, and you basically can't differentiate a lot in that. No, I'm not up with the play in terms of NMR. This may have been improved a little bit. I know that I was involved in some work where we tried to refine this by trying to get rid of some of the iron that causes this amalgam of peaks. But the problem is that you use the chemicals, and they actually not only strip out the iron, they strip out the phosphorus as well. So, so if we could get that, that would be really good. If we could do some more in situ work. The other thing, and it was quite amusing when I saw some recent work on molecular weight analysis, because I did molecular weight analysis when I did my PhD, because the head of the department that time happened to be a guy called Roger Swift, who was a sort of guru of molecular weight fractionation of organic matter, and he persuaded me to have a look at this technique. And it's a lot of fun. It was a lot of fun to do, put the stuff through a Cefidex gel and work out the molecular weight. And we did see some changes with time, but not with treatment, using high and low molecular weight. This is a bit unintelligible, but it shows you, it's just, the point I'm making here is that when we look, I wanted to mention something about water and something about fractionation in water, in terms of looking at at phosphorus and water. And basically the idea what you do is a physical fractionation. You can talk about an unfiltered sample, this could be a leachate or a water sample, or you can talk about a filtered sample commonly through 0.45 micron. And then you measure inorganic phosphorus and you measure total phosphorus. And you can end up getting, I don't know how many fractions you can end up with in the, it's about 10, Phil, or if you go all the way through it. It's quite complicated. The point about this study was that this was a study that we did in New Zealand, where we were looking at disposal of waste from dairy sheds, it's dairy shed effluent, and we're measuring, when you added this stuff to the surface, what came out at 70 centimeters. And what we measured was a lot of what's called particulate P, and the assumption was that particulate P was inorganic phosphorus. But we proved by NMR and also by adding enzymes, and this was mentioned the other day, that it was actually mainly organic phosphorus. So this shows you that organic phosphorus is actually quite mobile in soils as well. But it illustrates the technique that you can actually use a physical fractionation, but you also can use adding enzymes to identify organic phosphorus. Because you add the enzyme, and if you get an increase in inorganic phosphorus, you actually pick up there's indication of the presence of organic phosphorus. So that's the method. That's the sort of methodology out of it. Then we look at the sort of dynamics of the flux. How do we do this? And thanks to Alan, I've used this diagram so often. I think it's really, really good. It's one of the best diagrams I've found. I'm not just saying that because Alan's here, because it actually has quantities in here. This is kilograms per hectare in agricultural systems. And you can see that the eye of the needle here is soil solution. Everything has to go through the soil solution, which at any one time will contain 10 grams of phosphorus. So it has to be continually removed to let the plant get the 10 to 30 kilograms. And in most soils, you've got 50% in the organic pool, 50% in the inorganic pool, and the organic pool. And they all interact together. And in here, it's labeled microbial, but you'll notice there, it's actually got fauna in there as well. So this whole biological may only contain 10 to 30 kilograms, but it's the engine room. It's the biological engine room that keeps this whole system actually moving. So we can identify the poles and we can characterize the forms, but it's actually getting an idea of how these things actually move and how they respond to management and whatever, and climate and all sorts of variables. So we're looking at the processes of mineralization, for example. And McGill and Cole, and people were talking about stoichiometry the other day, McGill and Cole put together a sort of, what they didn't call it a meta-analysis then, but today it would be called a sort of meta-analysis of really stoichiometry in terms of and phosphorus and soils, not phosphorus, just carbon, nitrogen, phosphorus and sulfur. And they came up with this proposal, this hypothesis, that basically organic nitrogen mineralization was linked to carbon. In other words, it was linked to energy, which is biological mineralization. Whereas organic phosphorus and organic sulfur that's in the sulfate form is actually specifically related to enzyme activities and called biochemical mineralization. Now we know that it's not necessarily that simple, but it was a good basis, and it's a good model to actually look at, a good model system to actually look at. So the role was that basically plants and microorganisms just basically released phosphorus from organic phosphorus in response to demand. Whereas here it was driven by energy and it got nitrogen. And so if you look at that, this is a diagram where the decrease in soil organic phosphorus, sodium hydroxide extractable phosphorus, and looking at phosphatase activity. And you can see here that when you're not growing any plants, you don't get much enzyme activity, you don't get much drawdown. But as you grow different plants, you can see it's a really neat diagram that shows the role of enzymes in terms of mobilizing organic phosphorus. But there's also this negative feedback idea, is that plants and microbes investing incredible amounts of energy and nutrient in putting out enzymes. And when nutrient availability is low, they'll pump out the enzyme, mobilize the organic phosphorus, in this case nitrogen as well, and then the kickback, it feeds back and turns off the enzyme production. The thing about this stuff, and the reason why I put that in, is that we now know that, for example, nitrogen mineralization is actually partly driven by specific enzyme activities and not just related to energy. But another thing to illustrate that again is what the ecologists call the nitrogen fixation conundrum, which is that in temperate boreal forest systems we've got nitrogen poor, but there's hardly any nitrogen fixing trees. Yet we go to the tropics, which are nitrogen rich, and they're full of nitrogen fixing trees. That doesn't make any sense. Why? They're short of nitrogen. These guys are full of it. Why are they then fixing? There's a number of hypotheses that have come up. First of all, to explain that the temperate one is basically, it's the nitrogen fixation is limited by temperature. That's fine. That doesn't explain what happens in the tropics. So the idea in the tropics is that the reason why, because they're P-limited, and the reason why plants, actually nitrogen fixers are so dominant and they actually exist there, is to actually acquire phosphorus, because they need that nitrogen to make phosphatase enzymes to put that into the soil to get the phosphorus. So that's a slightly different take on the role of phosphatases in the production system. I'm going to skip that one. This is another one, which again, there's a lot of data here. But the other thing about trying to measure flux is to look at changes in poles over time. So this is a study that was done over a 1-year period, basically just looking at microbial phosphorus and different phosphorus fractions to try and get an idea of the movement within the system of phosphorus. And you had a grassland soil and an adjacent forest soil. And even though the organic phosphorus was 30% less in the forest soil than the grassland soil, the turnover rate was 40% higher. So even though the forest had less organic phosphorus, less microbial phosphorus, the turnover rate was actually higher. So it shows you that looking at just fractions only gives you part of the story. You've got to look at the dynamics a little bit. Another technique that can be used to quantify organic phosphorus is actually isotopic exchange kinetics, which is mainly used to look at, it's a sort of alternative to, it's a fractionation method, which relies on looking at the reaction of added inorganic phosphorus to soil. So you can identify different poles. But you can also use it to measure mineralization. It's a very involved technique. It's not nowhere near a routine. And this is an example of a study where we're looking at green manure growing maize, and they were looking at a lupin green manure, a legume green manure, and after 2 cycles, you can measure the mineralization in an incubation experiment. And what you find is that by adding green manure, by growing a green manure crop and putting it back in, you stimulated biological activity, and you actually increased the gross mineralization by 5-fold. So it shows you that benefit of that. So that's a technique that can actually be used. It's essentially isotopic dilution. And then we come to my favorite story, my favorite area of working, which is chronosequences. And a much better version of this diagram was put up yesterday. I must get a copy of that, actually. Where basically the old Walker and Sayers model, in terms of soil development, total phosphorus, by the time you get to the phosphorus limited stage here, you've basically got a lot of recalcitrant minerals and organic phosphorus. So the idea is that what is sustaining the system through here? What is the role of organic forms of phosphorus? And that was a question that we tried to answer. And luckily we managed to get this motley crew here, managed to lock us in a room in Perth for what, 5 days, was it? Or 4 days. And we had to try and come up with some new ideas in terms of explaining the role of organic phosphorus. And I don't know if I've got time. This is the last one anyway. But what we did was, and actually it was mainly Jonathan here who came up with the idea of, this is actually drawn to scale, and these are the different forms of phosphorus. I'll take this one here to give you an example. The grey one is actually calcium phosphate in rocks. The light blue is calcium phosphate in soil, apatite, and the dark blue is actually iron and aluminium phosphate. So this is inorganic phosphorus. This is plant phosphorus, biomass phosphorus. This is organic phosphorus. This is microbial phosphorus. And it's all drawn to scale. And this is 5 years, 1,000 years, 12,000 years, 120,000 years. So you can see through here, you get depletion of the inorganic, the rocks are even dissolving, right? And you'll see, but by the time we get to here, there's actually starting to decline in terms of organic and biomass phosphorus. But look at the role the microbial phosphorus here. By the time you get here, there's about 4 times, 5 times more phosphorus in the microbial biomass than there is in the plant biomass. And the reason why I put this up is to, when we're talking about organic phosphorus, we have to remember the microbes and also the other biota that are in the soil that are absolutely crucial poles that drive biogeochemistry. And this was a genuine surprise to us when we put it together. All right, Ben? It really was. And we nearly got it into nature, but didn't quite get there. So anyway, in terms of conclusions, I mean, what am I going to conclude? I'll just give you my perspective. I think we've got a pretty good handle on extractable organic phosphorus. Methodology has its limits, and I think we always have to remember that any methodology has its limits, and you've got to be careful. I think where we're lacking, and where there's a lot of work still to be done, and it's very complex, and there's no criticism of anybody, is this looking at the turnover and the flux in terms of trying to work out what's going on there. The interaction between the biotic and abiotic poles, and the role of extracellular enzymes, not only just the enzymes themselves, but where they come from and the expression. And I think that's that, and as new techniques are coming in and being developed, then hopefully we'll be able to open that up a little bit. And as I say, if we could get away from extractable, that would be actually quite good. But I don't see much of a chance of that in the future. But anyway, as Ben said, I've been around for a while. Still got a wee way to go. I'm not jumping off anytime soon. But one thing I've done is that I've done this with a lot of help and a lot of good people. Some not so good people as well, but no. But this was my PhD supervisor, Quan Go, who actually taught me a lot. And like a lot of good supervisors, I didn't realize how good it was until after the event. And you can see you see a certain character pops up a number of times here. Who's that? That's Phil and Ben, right? And also Richard McDowell as well, Holm Thiessen, Emmanuel Frossard, who I'm surprised wasn't here, and Ben in the helicopter, right? You get to go some interesting places in this game. So anyway, I'll leave it at that, and you can ask me any questions if you want, and I'll give you my opinion if you want as well. So.